thank you all for coming and welcome to this September 15th AME Graduate Student Community Seminar. We have once a week, and the GSC leadership team is a lot of the people you see on here. We are student volunteers who arrange seminars and other events like the International Food Festival and a spring picnic. We have meetings at Friday. The time is a little bit adjustable. We are currently having them via Zoom. Please contact Rachel Bennett or Roshana Nam for Zoom meeting invite if you would like to participate. We also would appreciate if you would become a member on Engage, so you can use the QR code or some other methods to join. We have a Facebook page, and we have a YouTube channel on which we put our webinar videos up on. Next week, on the 22nd, we will be having Zahid Sadiq, who I believe is a assistant dean for research at the College of Engineering, and he will be talking to us about College of Engineering research initiatives. After that, the week after, on the 29th, we will be having Rebecca Kerfess from Oak Ridge National Laboratories to be speaking on these polymer support structures. Please come and attend those also. Today we will be having Professor Hiroshi Ozawa, who is a new professor here at the School of Aerospace and Mechanical Engineering, and he will be talking to us about frontier research and issues in high-speed aerothermodynamics. Please join me in welcoming him. Thank you, Dr. Ozawa.
Okay, can I start? Okay, so
you'll have to stop sharing your screen, Robert. You'll have to, yeah, go ahead. Go ahead, Hiroshi. Share your screen.
Okay, can you see the screen?
Yes.
All right. Yes. Okay. So today I will talk about the frontier research issues in high-speed thermodynamics. This is a very broad topic, but I will try to focus on my research. And yeah, thank you so much for attending. This is an outline of this talk. And first of all, I will introduce about the hypersonic thermodynamics briefly. And after that, I will show about temperature sensitive paint. This is optical diagnostics for high-speed aerothermodynamics. And then I will show the aerothermodynamics research using TSP and PSP, these are optical for diagnostics. And I will show 4 results. And then finally, I will show the outlook of the hypersonic research. This is a typical hypersonic phenomena around the hypersonic vehicle. And as can be seen, can you see this current? No? Okay. All right. Okay. So once the vehicle flies much higher Mach number, And then first of all, the strong shock wave is formed around the body. And then first of all, there are several phenomena which has not seen in low aerodynamics. For instance, please see the leading edge of the vehicle. The strong bow shock is formed, and also the around the leading edge of the blunt body, the strong normal shock is formed. And then behind the strong normal shock, then temperature and pressure increase drastically. And then with increased Mach number, this distance from the blunt nodes to the shock wave becomes very small. And then which means that pressure and the temperature increment is much, much higher than low Mach number. And also because of the approaching the shock wave to the body, the boundary layer approaches the shock wave. And also behind the shock wave, the entropy layer created. And further, the shock wave approaches the boundary layer, then the viscous interaction occurs. And also then behind the strong shock wave, the dissociation and ionization occurs. And then maybe everyone knows that there is no fundamental fluid dynamics. It is, I mean that there is no ideal flow, but real flow is formed around the body. This is a typical physics of the hypersonics, but the actual model is slightly different. This is one of the example of the hypersonic vehicle, and this is a X-43. And then in actual body, there are various aerothermodynamics phenomena. For instance, so external flow field airframe, in which the heat transfer is very, very important. And also around the body, the transition occurs, laminar to turbulent boundary layer transition occurs. And then in the developing phase of the vehicle, the transition location should be predicted. And then also the turbulent modeling should be developed by simulation. And also, as I said, there is no ideal flow field around the body. This is a high temperature gas effect exists around the body. And also the forebody and external curve. As I said, turbulent transition to turbulent occurs. Once the boundary layer transition occurs, the heat transfer increases drastically. And also this vehicle flies in hypersonics, therefore a shock wave generates, so that shock interaction occurs. This shock interaction phenomena increase also heat transfer drastically. And for instance, the maximum heat transfer due to the shock interaction exceed the stagnation point heat transfer, which is more than 20 times of the stagnation point heat transfer. And then here, the air goes along the compression corner and just before the inlet, and then compressed air goes to the combustor, and then just before the combustor there is a inlet, and then at the inlet shockwave boundary layer interaction occurs. This phenomena also causes severe heating load, and also the boundary layer transition occurs. So that to realize such an actual vehicle, there are many of aerothermodynamics phenomena, and that has to be investigated in advance. So briefly, we can summarize why the hypersonic research is important. So as I mentioned, in hypersonic flight, the vehicle suffers from severe heating load due to the laminar to turbulent boundary layer transition, also the shockwave boundary layer interaction, and also the shock-shock interaction. And so these phenomena causes very severe heating load, so that in developing phase, accurate heat transfer measurement or estimation should be carried out carefully. And to conduct such experiment, we employ the very short test duration high-speed wind tunnel named shock tunnel. And then in this facility, the typical classical measurement technique is used, like thin film gauges or thermocouple or coaxial thermocouples. And these are very reliable traditional sensors. However, to mounting many of these sensors are very, very difficult because of the wiring. Therefore, they are an optical for diagnostics for global heat transfer measurement, satisfying high spatial temporal resolution becomes paramount. And the one of these optical flow diagnostics candidate is a temperature sensitive paint. Okay. And then people think that what is a TSP? TSP is a temperature sensitive paint, and then which has a very strong potential and reliability, and which is a key technology for high-speed aerothermodynamics research. So TSP is molecular-based imaging technology, and then which is a non-intrusive optical flow diagnostics. So in TSP measurement, the nanosize of luminophore works as a temperature sensor, and these various nanosize sensors distributed on the model. And this luminophore has specific physical properties as following. For example, each of luminophore has specific absorption emission wavelengths and also lifetime, and also quantum efficiency, which is relating to the emission intensity, and then Stokes shift, which is the peaks or the peaks between absorption wavelengths and emission wavelengths. And the thermal and oxygen cleansing. This is how to say? This is the technique of the pressure and temperature sensitive paint, and also thermal photo degradation. These are the how to say? These specific properties is very important in each luminophores. And then the TSP consists of luminophore and binder. Binder is used to fix the TSP on the model, and the solvent. And these have physical compatibility, and the physical property of the luminophore in TSP behaves in differently from the above. But therefore, we can make TSP, in-house TSP. So this is a typical calibration result of TSP measurement. So please see first left-hand figure. This is a emission spectra of certain TSP luminophore. So as can be seen that the peak of the emission is around 610 or 620 nanometer, and then the intensity decreases with increased temperature. And then we extract the intensity in each temperature and integrate it and plot their intensity, and we can get right-hand side figure. And once we get temperature calibration curve as shown in here, we can get once we get this calibration curve, then if we know the intensity from the TSP signal, then we can convert from intensity to temperature. And once we obtain the temperature record, we can calculate heat transfer. This slide shows a typical TSP setting. And first of all, we see the left-hand side figure. This is the spectra of the emission, absorption, and excitation wavelengths. So in actual, the green line shows absorption wavelengths of the luminophore, and the red signal is emission spectrum. And blue is excitation light source wavelengths. And then please see the right figure. First of all, I have to mention one thing, that in TSP measurement, the model should be fixed in the camera, on the camera. So we need, in TSP measurement, we need reference image and a test image so that the model should be fixed during the test time. So once we make TSP layer on the model, the created TSP layer is excited by excitation light sources and emit emission wavelengths, and detectors such as high-speed camera want to detect some specific wavelengths from the TSP layer. Then some of the bandpass filter should be employed. And then bottom figure shows the TSP construction of the TSP layer. So this is a typical TSP layer that I create. On the model surface, the insulator and binder plus luminophore layers is created, and total thickness might be around 100 micrometer. But the important is the TSP layer thickness. And then I will explain why this TSP layer thickness is important. So the left top is window of image, and the left bottom is a window on image. And once window tunnel start, and then the heat inflow penetrate from top to bottom in TSP layer. So this is a problem. Ideally, the sensor wants to measure only the temperature on the surface, but the TSP measurement has its layer thickness. Therefore, the discrepancy between the heat discrepancy or temperature discrepancy between layer top and bottom is different. So which causes a heat transfer error. So in actual, as I said, we want to know, or we want to record the surface temperature. But as I said, in TSP measurement, the averaged temperature in TSP layer is recorded so that the average temperature is smaller than actual surface temperature, and then which result in error of the heat transfer. And the right-hand side figure shows the effect of the layer thickness. As can be seen, an horizontal axis shows test time, and the normal axis is normalized heat transfer. And then, as can be seen, longer test time produce inaccurate heat transfer. And also the thinner TSP layer produces accurate heat transfer. So then ideally, the thinner TSP layer thickness is preferable, but thinner thickness TSP layer can produce very weak emission intensity. And then from here, I will show the TSP application to hypersonics and also the non-stationary aerothermodynamics. So as mentioned in introduction, to conduct such hypersonic test, the very huge size of window tunnel, shock tunnel, or hypersonic or high entropy shock tunnel is employed. This is a high entropy shock tunnel in DLR, where I have researched there. Like this shock tunnel can produce the test duration of millisecond. And also this window tunnel produce hypersonic and high entropy flow so that self-luminosity occurs as shown as seen in re-entry vehicle. And also the this type of window tunnel employs diaphragm to produce high pressure and high temperature. So the ruptured diaphragm produce the dust in the flow. So these three things are difficulty in high entropy hypersonic shock tunnel. And figure 2 shows reservoir pressure. And so this type of window tunnel should have to produce high temperature and high pressure. And as can be seen, that total pressure at reservoir location is more than or larger than 10 megapascal. And then test duration is as seen here, 2 or 3 milliseconds, but which depends on the test condition. And also, as mentioned, the such a high temperature, high pressure flow create the self-luminosity shown in the figure 3. So, as seen in figure 3, the very strong self-luminosity are generated. This signal becomes a very big problem in GSP measurement, because GSP measurement is optical for diagnostics. So this optical signal disturbs the signal from the TSP. And then TSP applied to the hypersonic cone in Mach 7 to detect the transition point. And then the TSP coating is produced partly on the cone. And then, as can be seen in left bottom figure, the TSP could detect transition point. And also the thermocouple measurement shown in the red color shows very, very good agreement with TSP. And the very big advantage in TSP measurement is that two-dimensional optical for diagnostics, so that we can see where is the transition location as shown in figure, right top figure. And then as seen in figure, that transition shows non-homogeneity and jaggy front, and also the stripe flow structure is clearly observed. And also surprisingly, in this test, we employed high-speed camera. with almost 100 kilohertz, and then transition location varies in time. So I said that the transition phenomena is non-stationary. And also we applied the TSP, the scramjet engine intake lamp, and then then the applied TSP clearly showed the transition location. Also, the heat transfer increase due to the shock wave generated from the sidewall. And then this is very important information because in designing the scramjet engine, because in the location of combustion chamber, the flow hopefully should be turbulent to increase the temperature and the pressure using the many of the vortices, so that in designing phase to check or to detect the boundary layer transition is very, very important. Okay, and this is a slightly different story. This slide shows a shock tube experiment. The shock tube is used for non-stationary aerothermodynamics, and which can generate shock wave. And the the system is very, very simple. Just divide the high pressure and the low pressure. And then, as can be seen, as shown in right top illustration, the driver tube has high pressure, and in driven tube there is a low pressure, and between two sections there is a diaphragm. And once diaphragm ruptured, the shock wave running downstream. And then this shock wave speed and the shock wave condition is easily controlled by changing the pressure ratio and the temperature ratio, and control the shock speed and the reflected shock speed and so on. And then what we want to see in this test is to detect the shock wave by TSP. And then in this test, the shock speed is around 900 meters per second. I'm sorry, not this is SI unit. And then so shock wave running downstream. But if we see at certain point of test section, and then we can see the shock wave running from left to right. And on the wall in the shock tube, behind the shock wave, the boundary layer developing in time. So then we tried to detect the shock wave, also the aerothermodynamics around the mounting cylinder. We placed the very small cylinder on the shock tube wall, as shown in the schematics, so that the flow comes from left-hand side, and then some phenomena occurs around the cylinder, and we try to visualize the aerothermodynamics phenomenon on the wall. Okay, so the top figure is a Schlieren image. Schlieren image shows density gradient, so which is usually employed to visualize shock wave, because shock wave behind and before shock, how to say, shock wave generate very steep density variation. And the bottom is TSP measurement. So the discrepancy between top and bottom result is top one schlieren image shows a spatial gradient, and the bottom is the surface temperature and heat flux. Okay, and the flow comes from left hand side. So TSP could visualize the non-stationary flows and also the incident shock waves and also turbulent boundary layer transition. And we can easily find out that where is the high heat flux. And also we can compare the flow field in a space and also the surface. That's again. So all right. So anyway, the which demonstrated that the TSP can respond in 1 millisecond. And once we obtained two-dimensional heat transfer distribution or heat transfer images, and we can make various figures, okay, such as XT diagram. From this XT diagram, we can easily understand where is the incident shock wave and the reflected shock wave, and also the boundary layer transition location, and where is the peak heating. And from a single image, also we can extract the heat transfer distribution along the line. So the left top image is the laminar case, and the bottom one is after the boundary layer transition. And then we can easily find out the flow field shows absolutely different trend. And then as mentioned, once we obtained this image, we can plot the heat transfer distribution as shown in right top figure. And also we can, so if the temperature or heat transfer variation extracted at certain point, then we can create heat transfer variation as shown in right bottom figure. So that, yeah, so then once we obtain the two-dimensional image, we can extract many, well, we can obtain many of the information. And this is a not hypersonic application, but application to the TSP application to low wind tunnel testing. We applied also TSP for swept low speed laminar wind. And so as you know that in hypersonics, the surface temperature and surface heat transfer becomes very high, but in case of low speed flow, the surface heat transfer is very, very small, almost negligible. Therefore, we have to do some special trick for this case. And then we successfully visualize the laminar to turbulent boundary layer transition location, and also the because of the wing, swept wing, the cross flow vortices is generated. So cross flow vortices also be visualized by TSP. And also we are interested in high speed pressure sensitive band. So in case of temperature sensitive band, which is the emission intensity is changed by the thermal quenching. While the pressure sensitive, in case of a pressure sensitive paint, the pressure sensitive molecule or luminar is changed by the oxygen quenching. So the density of the oxygen effect on the emission intensity from PSP molecule. So the high speed, so developed high speed pressure sensitive paint applied to the applied for the hemisphere model, as shown in this picture, and put it in a shock tube test facility. And left side shows schlieren time record, and the right hand side is PSP record. So PSP showed certainly non-stationary pressure distribution, and also this result demonstrated that developed PSP is able to respond even in one millisecond testing. Okay, this is additional information. I transfer all of my facility from the previous university, Tokyo Metropolitan University, and so the hypersonic shock tunnel of the Mach 5 is transferred in the end of this month. And also the surrounding facility high-speed cameras in the cameras lasers and measurement facility of Deuteron. Also the various facilities, these are transferred to the OU. Okay, this slide shows the outlook of the my research, also the hypersonics, and one is the TSP high entropy hypersonic flows. As mentioned, the Mach number increase and the entropy increases, then self-luminosity intensity stronger. Then this luminosity disturb the signal from TSP, so that this problem should be solved. And second is hypersonic boundary layer transition. This is a very important topic, and so boundary layer transition research has been carried out since 100 years ago, but hypersonic boundary layer transition is slightly different from low speed flow because different type of transition occurs. So that the important is how detect where the transition location, or how to predict the transition point. And the most important is the analysis of the transition mechanism in hypersonics. And then TSP in free flight object. As mentioned before, the object, for example, the test model should be fixed in test duration before and after during test duration. But if the TSP is applied to even in moving model, then that is one topic. And the first is TSP and PSP application to actual model. For example, scramjet engine development, and also fuel combustion flow, and also the rotating object. For example, helicopter blade or turbine blade. The TSP and PSP is a non-intrusive optical flow diagnostics, so that there is very strong potential application to the rotating object. And also the research on shock induced flow like a shock-shock interaction and shockwave boundary interactions. Okay, that is all for my presentation. Thank you so much. Is there any question?
So when you're talking about the research areas in that last slide, are those things that you're interested in working on, or is this stuff you're interested in plus the broader challenges of this subfield? Because, oh. I may have been muted there. Dr. Lai has a question.
Yeah, please.
Yes, Dr. Ozawa, thank you very much for your presentation. It's very inspirational. I have a couple questions, if you don't mind.
Yeah, please.
All right. So I may be missing something here, but could you just explain for me? Okay, because that what I understand is that you are using TSP for measuring temperature, right?
Yeah, right.
The surface temperature, and so you are making the optical measurement of the surface temperature distribution, right?
Yeah, right.
Yes. And then in your slide, for example, your slide 11, what you present actually is a heat flux, right? Heat flux ratio. Okay, one with the TSP and the other one without. But what I don't understand is that because the temperature and the heat flux are two different things. Okay, so you got the measurement of temperature, but then how do you convert it to heat flux?
Ah, okay. Just a moment. Wait.
Yeah.
This is so can you see the left bottom formula? This is the formula for convert from temperature to heat transfer. Time variable heat transfer rate.
Okay, so this is at for the same location, right?
Yes, same location. Yes.
So you are okay based on the time. Okay, I see.
Mm-hmm.
Okay. Okay. Also, I have a question: is that to use this, you still need to do the calibration, right?
Yes.
And so, what I understand is that you are you also have a thermocouple, right? So you use a thermocouple for temperature measurement.
Yes.
So, so you are calibrated against the thermocouple readings?
So what do you mean that the okay, so
right. So
TSP,
what I'm saying is that how do you do the calibration?
okay, so just a moment. Also to calibrate TSP, I employed the thermocouple. PT100 is a thermocouple for calibrating the TSP. Yeah.
So what kind of thermocouple do you use?
To calibrate the TSP. PT100.
What type? What type of thermocouple?
So the thermocouple is in the calibration. Yeah, so that I said PT100.
Okay, yeah.
Yeah, platinum.
Okay.
Yeah, and but in the test, I don't use a PT100, but coaxial thermocouple is used in actual test in the wind tunnel testing. Some type of thermocouple is used.
Yeah, so what I'm saying that because you are calibrating against thermocouple, so the accuracy of your temperature measurement will be just about the same as a thermocouple, right?
Yeah, right.
Okay, yeah, okay, that's all my question. Thank you. Thank you very much.
Right.
Yeah, I have the same question. So you don't use any correction factors for the thermocouple?
No correction. But so that I do commercially the PD100 set the accuracy so that I use their accuracy.
What was the diameter?
Diameter
Ah,
of the thermocouple.
yeah.
It's I don't know, 1 millimeter.
Oh, 1 millimeter. So quite.
Yeah, but so just a moment, I explain in detail in TSP calibration. I employ the Peltier, you know Peltier? Peltier facility, and then to measure the temperature of Peltier, and I employ the PD100.
Thank you.
I have a question. I missed the beginning part of your presentation, but what I learned from Dr. Lai's question was you use TSP and then use some optical camera to collect the temperature profile, right? So what's the benefit of this technology compared with the infrared imaging, thermal imaging?
Okay. So first of all, you mean that infrared camera, you mean?
Right.
So first of all, we employ the high-speed camera, and that this is my guess, but as far as long as I know that infrared camera cannot record in high-speed frequency higher than 100 kHz or 200 kHz. Maybe few thousand hertz is possible.
So if the response time is not fast enough.
Yeah, right.
Okay.
Yeah, this is because window tunnel testing time is millisecond order, so that we have to employ much higher sampling frequency.
Okay.
Yeah.
That was my question. And
also the one thing that the TSP measurement, we can employ the luminophore, but each luminophore has specific temperature sensitivity, so that if we want to know very small temperature discrepancy or variation, we can employ much higher temperature sensitive luminophore.
okay. Thank you. Yeah, I didn't know enough about these two different technologies. Thank you for the answer.
Okay, I think I may have had my microphone on mute earlier. The topics you listed at the end, are those ones you are interested in working on, or do you also include some more general problems in aerothermodynamics?
You mean that the outlook?
Yeah. Are these all things that you're looking at personally in the future?
Yeah.
Okay.
But this is maybe part of my interest. Maybe there's another interesting topics.
Okay. You know, some of these were pretty fundamental, and I was kind of wondering, are these all the fundamental ones in this area, or are there some more fundamental ones that you didn't mention? that you're aware of?
Mhm. Yeah, right. Some of topic is very fundamental research, and some of topic is more application.
All right, I have one more question, if you don't mind, Dr.
Yeah,
Ozawa.
sure.
The question I have is on your slide 17, when you do the experiment on the sharp tube. Yes.
Yes.
Okay. In the video, I saw that after the sharp wave passed through the cylinder, right? And then sometime later, there's a backflow coming back from
Yeah.
line side.
Yes.
Can you explain why is that? Why there's a backflow, the bounce back?
Yeah. So first of all, so the test section is here, right? And after the shock wave passed at the cylinder, and a reflected shock wave coming back from the right-hand side.
Okay, so the sharp tube on the right-hand side is closed.
Yes, right.
Okay, so it's not it's just a discharge to the ambient, no?
What do you mean NDM?
I mean the atmosphere. So it's not a. So it's a closed tube.
Yes, closed tube. They are both sides is closed, completely closed, and so as seen in this configuration, the driver tube is closed, and also driven tube is closed. This is because to control the shock speed.
Okay, I see. Thank you.
Yeah.
Thank you.
Anybody else? Good, then Robert, we could probably say our thank yous and close the session.
Thank you all for coming, and thank you, Professor Ozawa, for speaking to us about this complicated topic that shows some of the way forward for some of these fundamental measurement issues in figuring out how hypersonic flow actually works, and also telling us how this is affecting the design problems in hypersonics. And thank you all to our attendees, and thank you for your wonderful questions. And I guess that's it.